recording. Okay. See, I know that there are some mathematics that need to cover when we go into like linear regression and like logistic regression. I would try to keep it simple, right? But inevitably, we will run into some of that. Okay. So now let's talk about the other type of model, which is the logistic regression. And say, when you look into this title, right, I'm saying that predicting probability, okay, predicting probability, because in logistic regression, it only predicts a y that had binary values, okay, which means that it's categorical, but binary means that they can only have two categories, right? Yes or no, good or bad, things like that, right? So, so when you are predicting like two categories, you are actually predicting the probability of each category, isn't it? Right? So if I'm predicting good and bad, right, the model, the model is actually a mathematical equation, right? So after the calculation of the equation, it will come out with a number, right? It cannot come out with like male, female. It cannot come out as like red and green, right? It would always come out something like the probability that y equal to 0, or the probability that y equal to 1, right? Okay? So actually predicting category is the same as predicting the probability of each category. Okay, let me say it again. This is very, very important. Okay? So the outcome of the model is always numeric. Okay? And when you are predicting category, you are actually predicting the probability of each category. Okay? That is the very, very first thing and the most important thing that you need to know when you are using model to predict category. Okay? There are a lot of model that you can use to predict category, and logistic regression is the simplest one. Okay? Just like you can have like 100 different models to predict numeric value, but linear regression is the simplest one. Okay? But in this course, we are using this simple model to give you an idea about how to use model to make business decision, right? That is the purpose of our course. So again, I will teach you how to do logistic regression, and you will see that the procedure to build logistic regression and the procedure to make prediction is almost the same as those of linear regression. Actually, in the R environment, whatever model type that you're using, I mean, when you are building like a decision tree model, you are building a AI model, a neural network model, the operation is always similar, right? It's always similar. So what you need to learn is how to like fit the data into the method and let the method do the model for you, right? So as long as you have the model, the way to predict, to do prediction with the model is like very, very similar to each other. Okay? So that's the thing that we want to learn from logistic regression. And then we want to know how to interpret the coefficient of logistic regression. Okay? And then after that, we will go into the topic that how to measure the model accuracy. right? And these are the two things that we already done with linear regression, okay? That we just want to do it again for logistic, okay? And the third thing that logistic regression is important is it is it has a very close relationship between the prediction and decision, okay? When you build logistic regression, okay, you will not build it for fun, right? You want to use the logistic regression to do prediction. And you want to use the prediction to make decision. Okay? Prediction is not the same as the decision, okay? And we will spend some time on this topic, okay? Actually, I think we cannot finish everything, all of this in a week, okay? So in this week, I will try to walk you through a few. After I explain the concept, I will walk you through a few notebooks, okay? And then you will do an assignment, and then we will continue our discussion next week, okay? That is the plan. Question? Okay, so let's move on. Now, as I already told you, right, in the aspect of building model and doing prediction, the code are actually very, very similar. I mean the two things. Although the linear regression is to predicting numeric, okay, and the logistic regression is to predict probability, but the way they operate are very similar to each other, okay? So when we are building linear regression, this is the way we do it, right? This is the code. And this is the data, right? And this is the method, right? And these are the model spec, right? We give this data frame to this LM method, right? And we tell it that we want to use x1 and x2 to predict y, right? Okay, this is the model spec. And then this function call will return a model, okay? So this is important, right? You need to know that LM is a method, okay? Data is the data that we fit into the method, right? We fit the data into the method and tell the method that this is the model spec, okay? And then this method will create a model for us, okay? So now this is for linear regression, and if we want to do the same thing in logistic, we will change LM to GLM, right? This is the first difference, okay? It is using a different method. It's called GLM, okay? And besides data and model spec, you also want to specify the family, okay? Actually, this GLM method can build many different model type, and logistic regression is just one of it, okay? And because it's so sophisticated, it can build like many different model type. So when you use this GLM to build logistic regression model, you need to specify family equal to binomial, okay? So this is just you change LM to GLM and you add one argument, family equal to binomial, okay? And of course the y here, it has to be a binary variable, okay? I told you, right? The logistic regression can only do, it can only predict like categorical variable of binary value, right? Good or bad, yes or no, things like that, right? So usually we will encode this binary categorical variable into 0 and 1. Let me say that again. The logistic regression can only do with binary categorical data, okay? So, and because they are binary, so usually we would encode the binary things into 0 and 1. It would make our mathematics easier, okay? So if it was good and bad, then we would encode good as 1 and bad as 0, okay? So later on, when we calculate the probability, we will say that we want to calculate the probability that y equal to 1, which is the same as that y is good, okay? So that is a way of encoding to make our mathematics easier, okay? Because it's binary categorical variable, so we like to encode them as 0 and 1, okay? Now, so after we build the model, we want to examine the model, right? So we are using this function summary. Now, it's the same. The summary function is the same. It applies to, this is M1, right? So it's a linear regression model. And M2 is actually a logistic regression model, right? But when you want to summarize them, you are calling the same function. Okay? Same function. This function is the same. And in this function, you will see that it will also give you, for every x, there is a coefficient. Okay? And then you want to like verify the data, right? Or you can say that you want to do the prediction. Okay? If you want to do the verify, which means that we want to verify the y hat with the y in the training data. Okay? By verify, I mean that we are not using this model to predict new data. Okay? We are using this model, we are examining the difference between the predicted value within the training data. Okay? That's what we call verify, right? So when you want to verify the y, the difference between y hat and y within the training data, you don't need to give it new data, right? Because within this model, the training data is always there. It's already there, right? So when you want to verify y hat inside the training data, you will do predict M1, right? Okay? And then if you want to verify it in the logistic regression, there's a little different, okay? You are still calling predict, okay? You are still giving it the model, but you need to add one argument, which is type equal to response, okay? If you do not include this one, it will actually return 0 and 1, okay? But we want to see the probability of y equal to 1, right? Because here, we no longer want to predict the value of y, right? Instead of predicting the value of y, we are predicting the value, we are predicting the probability that y equal to 1, right? Okay? As I tell you, the categorical model, they are predicting the probability of each category, okay? So instead of predicting y itself, we are predicting the probability that y equal to 1, okay? And in order to do that, in this predict function call, you need one more argument, which is type equal to response. You got it? Okay? And then the last one, when you want to do the prediction, right? You want to do a prediction, it means that we want to use the model to predict some data which is out of sample, right? So in this case, you will have some new data, right? You will give this new data to the predict, and then you were like, usually in this new data, you do not have y, right? You only have x. So you give the x that you know to this predict, and you would predict the y value for you. Okay, still y hat, right? And if you want to do the same thing in logistic regression, again, you need one more argument, which is type equal to response. Okay? So you can see that the procedure of doing modeling and predicting are very similar in linear regression and logistic regression. And actually this similarity applies to almost all types of models. I means when you're doing like decision tree, when you're doing a numerical network, when you are doing like random forest, I tell you that they are like hundreds. There are more than 100 model type in today's data science. Okay, and all of like most of this model type, they are predicting either numeric or categorical target. Okay, so there are different methods that will produce the form of model are different, but the function of the model, they usually are the same. Okay, the decision tree is a tree. It's no longer a linear combination of x, right? Neural network is actually a network. It's no longer a linear combination, right? But the functions are the same, right? Okay? After you build the model, okay, you can give the new data to the model, and you still call this predict function, and you can use the model to do the prediction for you. Okay? So this like modeling, examining, verifying, and predict, this procedure like applies to almost all type of model, almost all type of methods. Okay, and that's why in this course we start with like just two model type. Okay, and if you want to learn more about the modern data science, there are a lot of models that you can learn. But whatever model it is, their functions are almost the same. Okay, it's to predict either numeric y or categorical y. Okay, and the procedure are almost the same. Okay, it's like this. Okay, you get me? Okay. Okay, let's look at take a closer look at linear regression model, right? Okay, so this is linear regression model, right? And have I told you this before? I say that linear regression model is the simplest and the most difficult, and it is the less precise yet the most useful. Have I said this to you last week? No. Looks like okay. I'll do that again. Okay. Actually, this linear regression. Every model has a form, right? When you are using x to predict y, then you must have the form. You must have the function. You must define the function so that you can calculate y hat with x, right? So the linear regression is simply the linear combination, right? So it has a bunch of coefficients, and you multiply the coefficient to the value of x, and then do the summation, right? That's actually the easiest model form that we can ever think of, right? So it's actually very simple. And because it's simplicity, it's actually less precise. I told you that there are a lot of model, like decision tree, like random forest, like support vector machine, like gradient boost. Like I can say, and every model has a lot of different variation, right? There are hundreds of models that can be used to predict numeric y. Okay. And among all of the models that predicting numeric y, linear regression is the less precise one. Okay, it means comparing to the modern big data, machine learning type of or artificial intelligence model, the linear regression model is less precise, which means that it has a larger average error and it has a smaller R square. In comparing to the modern data science method, such as like decision tree, such as like numeric network, machine learning model, okay? It's less precise, but actually it is most useful, right? Because this linear regression model has a very unique feature, I should say. Okay, it has a very unique feature that the other type of model do not have, right? It's because this coefficient actually has a practical implication. Okay, it's less precise, yeah, which means that if you want to use this model type to do prediction, its accuracy is actually lower than the machine learning method. But it's more useful than the machine learning method because its coefficient has a practical implication. This B1, because they are predicting y in this mathematical form, right? So when x1 is increased by 1, right? Y would increase, the y hat would increase by b1, right? I mean, if x is increased by 1, okay, and y hat would increase by b1, right? It's simple, right? This is like primary school mathematics, okay? If xk is increased by 1, then y hat would increase by bk, right? Which means the coefficient is the marginal effect of x to y, right? Isn't it? Now let me cite a real example. Okay, so it would make you easier to understand, right? If the y is my revenue, okay, in a business context, y is my revenue, and the x1 is my advertisement expense on TV advertisement, and the x2 is my advertisement expense on Facebook, okay, and x3 is my advertisement expense on Google keyword advertisement, okay. So the x is different type of advertisement expense, right? And the y is my revenue, right? Okay. So I know that for each type of my advertisement, I can see its marginal effect to my revenue, isn't it? Right? So and these things only happen, this formula only happen in linear regression. Okay. The other type of if you are using like machine learning type of regression, machine learning type of method, your model cannot tell you this. Okay. Only the linear regression can tell you the marginal effect of x to y, right? And this is very useful. It's very useful in business context, right? So I know that if I can estimate this coefficient correctly, okay, right, I can tell the marginal effect of different type of advertisement, right, to my revenue, isn't it? And that is extremely important, extremely useful in business context, right? Okay, so that's what I say, that it's less precise. Okay, it will have a smaller R square, it will have a larger residual standard error, but actually because its coefficient do have a very important business implication, right? So it is very useful. Okay, and you got my point, right? And the way I say it, that it's simple is because this linear combination is very simple, right? You can I think you cannot conceive a simpler things, mathematical equation, right, than this one, right? This is very simple, but actually it is very difficult to have an accurate estimation of these coefficients. Okay. Now, in this course, I do not have the time to tell you how to do a correct estimation on this coefficient. Okay. In order to do this, you will need to learn. You will need to take the econometry course. Okay. Let me say it again. If you want to have a precise estimation of this beta, of this B, right? Okay. Like simply calling LM is not enough, right? Okay. Simply calling LM, it will give you this beta coefficient. But usually in the business context, you cannot trust this coefficient simply by doing an LM. Okay. You need to take the course of econometry. Okay. The course that you learned in your research method, right? The way that you learn in your research method, the way that you learn in your inferential statistic, managerial statistic, right, is not good enough to make sure that these coefficients are correct. Okay. If you want to make sure that this coefficient is correct, it's very difficult. Have you ever seen the textbook of econometry? It's like more than 100 page. Sorry, more than 1,000 page. Okay. Okay. So it is actually very difficult to make sure that this coefficient is accurate. Okay, and that is a discipline by itself. I cannot teach you in my course. Okay, so you need to be careful, right? Although it's very useful, I mean this B, you can basically use it as a marginal effect of X to Y. But that's subject to a lot of conditions. For example, the one thing, there's one simple check that you need to you can do is you want to make sure that the between the predictor, between this X, they should not have high correlation to each other, right? If the X has a high correlation, as high as 0.8, you can no longer trust the beta estimation in your LM model. Okay, and besides the correlation, there are lots of very tricky things that could make the coefficient bias, even maybe reverse the effect of your coefficient. Okay, so be careful with that. If you really want to use this like coefficient as the marginal effect of x to y in a business context, you always have to consult someone who has the econometry training. Okay, don't just like do a simple LM and just like trust it 100%. It's not sufficient. Okay, and this is the two things that we need to emphasize. And the same thing, linear regression model apply to GLM, which means that the logistic regression is still a linear model. Okay, I mean the logistic regression is still using a linear combination of x to predict the category of y. Okay, mathematical wise, the logistic regression is very similar to linear regression. Okay, now especially in the beginning, it is still using a linear combination of x, right? So you have x, so you use this. The model will estimate the beta for you, right? The method will estimate the beta, this b for you, right? So as long as you know this coefficient, you just do a combination of coefficient and the predictor, and then you will have a value, right? But the difference is right now you are predicting the probability of y equal to 1, right? Okay, instead of predicting the value of y itself. Okay, and in order to do that, you need to do a transformation. Okay, so the difference between LM, linear model, and GLM, generalized linear model, is that in the latter, in GLM, you do not predict y directly by the linear combination. Okay, you need to do a transformation on this f of x. Okay, the f of x is actually the linear combination of x, right? Right? You cannot predict y directly from this linear combination. You need to do a transformation. Okay, in logistic regression, we are using a transformation function called logistic, and that is why it is called logistic regression. You get my point? Okay, so logistic regression is still a linear regression. Okay, and the method is still estimate a set of coefficient that minimize the error. Okay, that in that part they are the same as linear regression. The difference is you do not predict y directly from this linear combination. Okay, you use a transformation function to transfer the sum of this linear combination into the probability that y equal to 1. That is the difference between logistic and linear regression. Okay? Okay? So the key difference is that you no longer use this linear combination to predict y directly. Okay? You use a transformation function to transfer this linear transvection, to transfer this linear combination into the probability that y equal to 1. Okay, and that is what it called, because the transformation function is called logistic. So So that is why we call it logistic regression. You get me? Okay. And in this page, you see some terminology, right? Some new terminology. Probability is the thing that we already know, right? Now you also see odd. You also see log it, right? Okay. So these are the two things that we need to explain. Okay. See, the combination is actually the logit of y equal to 1. Okay. Now, you know who she is, right? What is her name, right? Anyone? You don't know her name? It's like I mean, in the Matrix, in the movie Matrix, there's this character, right? So what is her name? No one knows. Now her name is actually Trinity, right? Trinity. Okay. So actually, odd and logit, all of these three things, they are probability. It's just like the definition of Trinity in Christian tradition, right? There's a Trinity, right? It's the Holy Spirit, Holy Father and Holy Son, right? I don't remember very well, but they are the same thing, right? They are not three different things. They are the same thing. They are the three different names of the same thing. Okay? So you can, probability is the thing that we know, right? So you can transfer odd. You can transfer odd from, in this equation, you can actually transfer probability into odd. Okay? And log it is actually the log of odd. Okay? So they are all probability in different way, right? Calculated in different way, right? So the P is actually the ratio of success, right? It's easier to understand. And the odd is actually P over 1 minus P. Okay? So the relationship between P and odd is actually, because 1 minus P could be very, very small, right? For example, if the P is 0.01, okay? Sorry, let me say it again. If P is very large, like 0.99, right? And 1 minus P would become 0.01, right? And because this is 0.99 and 0.1, so the odd will become 99, right? Isn't it? So if your P equal to 0.9999, what is the odd? I mean, if your P is 0.9, right? So 1 minus P is 0.1, right? So if your probability is 0.9, your odd is 9, right? If your P is 0.99, your odd is 99, right? So what if your P equal to 0.9999? What is the odd? Yeah, it's 9999. Okay, so odd is actually just the other name to express probability. Okay, and its value is from 0 to infinity. Okay, it's no longer like probability is between 1 and 0, right? Okay, the range of odd is from 0 to infinity. Okay. And this logit is just to place, is just to apply logarithm, the logarithm, natural logarithm, okay, natural logarithm on R, okay. So it's like log P1 minus P, okay. So the value of logit is actually from negative infinity to positive infinity, okay. So as long as you know P, you can very easily calculate O, and you can very easily calculate logit, okay, right? And well, and vice versa. If you know O, you can calculate P. If you know like logit, you can actually use this function to transfer the logit back into P, right? I will spell the mathematics. It's actually very easy mathematics, okay? So they can transfer to each other, right? Because they are one-to-one monotonic, right? And they are the trinity of probability, okay? So the reason that we need to define art and logit, okay, when we are doing logistic regression, the reason that we need to define art and logit is because the linear combination now becomes the logit of y equal to 1. Okay? And the coefficient is actually the art ratio. It is no longer the increment of y. Okay? Because it has the real practical implication. It has the practical meanings. When we are using logistic regression, it's easier to express probability by logit and art. Okay, it's easier to do so because the linear combination is exactly equal to the logit of y equal to 1. Okay. And when we want to estimate the marginal effect of x to y, it's no longer that x increase by 1 and y would increase by 1. Y would increase by b1, right? It's actually need to this coefficient is actually implied to the art ratio instead of increment of y. Okay. So the reason that we need to define these two different measures of probability is because that it makes us easier to understand and to use logistic regression. You get my point? Okay. So logistic regression is still it is a linear regression, but instead of using a linear combination to predict y, it actually need to use a transformation function, right? To transfer the linear combination into the probability of y equal to 1. Okay? Which means that the linear combination is actually equal to the logit of y equal to 1. Okay? And it also has the feature that the coefficient in the logistic regression it implies the marginal effect of x to y. Okay? But it's no longer the increment of y, okay? Because we are talking about the probability of y, right? It's no longer the increment of y. This coefficient, it implies the art ratio of x marginal effect to y. I will explain that later, okay? Okay, and that's why when we get into, before we get into the detail of logistic regression, we need to define a probability in 3 ways. Okay? Okay? And these 3 ways, they have a 1-to-1 monotonic transformation. You know in one of them, you can calculate the other 2. Okay? Okay, so this is the this is basically the mathematics that we need to know about the logistic regression. Okay, this is basically the mathematical thing that we need to know about logistic regression. And let's take a break, and then after the break I will walk you through a series of notebook, right, and start to use R to help you understand and also like apply the logistic regression to business applications. Okay? Okay, let's break and let's be back at 10 after 11. Okay.